Our speaker, someone who has had a very long and distinguished career in computing. I won't say a lot about her background because there's lots of interesting information available on the web if you want to go look. But a few things that are notable. She started off with interest in becoming a math teacher. And like many of you faced with student loans, found an opportunity to work at IBM Laboratories, where she stayed for the next 45 years. So they must have done something right there. And so did she. Credited with a number of firsts. She's received many, many awards in the field, including election to the National Academy of Engineering, a fellow of the ACM, the Ada Lovelace Award, and most recently, the ACM Turing Award. So it is with great pleasure that I introduce to you Frances Allen.
Thank you. I think, my mic. I think I heard a roll of drums.
Part of our arrangement.
I'm really delighted to be here today, and also it's been a wonderful experience. SPAF set up a great visit for me, and so I've met with students, I've met with the dean, I met with professors, and we just had some of the faculty members. So it's been a great day for me. It's kind of a cross view of what is going on here at Purdue, and this is my first visit to Purdue, to the whole area, and I'm really impressed. And one of the things I didn't know is that Purdue had the first computer science department with graduate students in it. I always thought it was my alma mater, the University of Michigan, and maybe Pittsburgh. So anyway, I'm delighted to be here. And when I received the Turing Award, I knew about the Turing Award for about a month to 6 weeks before it was announced. And I had an opportunity in those 6 weeks to talk to members of the committee who had selected me. They called me on the first day, one after the other, and I also had an opportunity to think about what it meant. Well, what it has meant to me is that it's changed my life, but more than anything else, it's giving me an opportunity to talk about some things in our field that I feel very strongly about. And so I'm using this to actually talk about the need, and I'll give you the net of my talk right now, the need for new languages and new compiler technologies for performance. That is the area that I've worked in for 45 years, essentially, and compilers and languages, mostly compilers for high-performance computing. And I'm going to go through a bit of my career, but first I want to talk a little bit about something you all know about, though maybe not everyone, is the new challenge that we have in this area, and what are we going to do about it? The we is you, people. I'm not going to be able to make any changes at this point, other than get messages out that we really do have to change some things in order to meet the challenge that I'm going to put before you. So be prepared. You might get some new work to do. Okay. Parallelism, as you know, most of you know, is moving to the laptop and to the desktop. It's going to be universal parallelism. That's a word I picked up recently, a phrase I picked up recently. And parallelism has been the purview in the past of the high-performance computing systems in order to get additional performance on the applications that are particularly important in the high-performance field. Now, I'm sure that it's been used, and know it's been used, in other parts. I'm not familiar with databases. I am familiar a little bit with some streaming work that I related to, say, code breaking, because I was involved with such a project at one point. But my background in the area of high performance has been pretty much focused on the engineering, scientific high performance applications. Not on the applications, but enabling the performance. But what is happening is with performance moving to the desktop and to the laptop and being universal, is that we are being faced, those of us in languages and compilers, are being faced with a new challenge. And some questions I want to put before you are, how can we use these platforms and are new languages, compilers, and software systems needed? My answer, as I've already told you, is yes, big time. And I think we probably are not quite ready for that challenge. So I'll say a little bit about what's driving this change, in case you haven't heard about it, is that the end of Moore's law may or may not be in sight, depending on who one talks to. But frequency scaling is slowing dramatically, and in part because of the heat problems that the density is causing. So, and in order to overcome that, we are in the process of putting together more cores, more mini processors on the same chip, along with their memories, and so these are processors which are slower, or not going up the performance curve that we've been accustomed to, but which can where we can hopefully sustain the performance curve that we're used to by making good use of parallelism that's inherent in them. Let's see, I have to get this technology straight here. So, in other words, there's a gap in the Moore's law, the pink piece of which is the transistors shown in this slide, and the real performance that we're going to be getting from the technology. So what the question is also how is this going to play out? We're going to have parallelism at a massive parallelism, and here is one projection. There was actually a workshop here at Purdue last spring, and which I've looking at it on the information on the web, I found very, very interesting. And this chart I took from one of the presentations, with the permission, by the way, of the author, and got in touch with him. And so this is the rate at which we're going to get parallelism. You can think of cores as parallel as CPUs that are going to be executable in parallel. That's kind of a gross way of characterizing what the possibilities are. And it's going to roll out, I think, much faster than this. This is the projection that was that was made at that time, one of the projections. But what is going to happen is that the architectures themselves are going to change tremendously. And there's a lot of discussion going on among the architects about, come on in, you find a seat on the floor. Gee, it's like cores are already descending. We'll have parallelism everywhere. So we'll have in that particular talk that I had seen and talked to the person who had made this up from Raytheon, the projection was it would be 1,000 processors on the chip, and there'd be multiple of these chips by the year 2021. Well, we're well on the way to doing that already. In some instances, often and in particular special purpose architectures. So the question then is, how are we, the people in the software, in the business, we in the application enablers at business, how are we going to use all of this potential parallelism? And it has to be up to us. It's not going to, it'll be there. There's no question about it. It already is at an astounding rate. And so these multicores, or the parallelism, is already driving new architectures, and they're already finding some limitations there. Memories the amount of memory is being cut back. For those of you in the architecture business, that starts to get, or in the lower layers of the software stack, that is a problem. And out of this we get universal parallelism, and in order to drive the universal parallelism, we're going to have parallel programs that decide how to distribute the computations, how to map the computations to all of these cores. One of the popular ways now is to think about multiple threads. So you have multiple threads of computations running using from a single application running in parallel. Identifying what these threads are is another piece of the challenge. And there are a lot of papers. I just came back from a conference in the PACT conference in Romania, and many of the papers were related to threads generation and management. And then, in order to create the parallel programs, are we going to rely on all the students in the world to write them? I mean, this is a challenge to write these parallel programs. They're not easy to write at all. It can take a very long time, and we've got to go to new compiler technologies which will do automatic parallelization. That's my belief, and I strongly believe it. And I'll show you some of the background work that I had done over the years that leads to that belief. And in order for the compiler technologies to be able to do automatic parallelism, we're going to, of the codes, I absolutely believe we need new languages. And that gets very speculative as to just what the shape of those languages are, but it won't be extensions of C and C++. It just is impossible to go from there to getting the performance that is available from all of these cores. So it's parallelism all the way up the stack, and in fact a real earthquake is happening. So what I want to do in the next few charts, so in fact the core of my core here and for this talk, is to describe my experience related to this field, and as an aside, or at least part of it, is my early career, which actually was the primary reason I think I received the Turing Award. But so it's a dual focus that I have in this part of the talk, which will be most of the quite a bit of the talk. The other goal I have in this, besides, is to look at our history. We're losing our early history. The history of our field is often the history that started when you started. That's the way we tend to think about it. And I heard somebody at a conference, the FCRC conference, say, I started 20 years ago. Before then, all the machines were simple. After that, they were complicated. And I thought, this is a piece of history that this talk will, I hope, dissuade you from, because early machines were very, very complicated. Anyway, I'm going to talk about two or a few projects. First of all, I want to talk about Fortran, which I was glad to hear today is still alive and well here. And talk a little bit about, that was done in between 1954 and 1957. 57 was when I joined IBM, and my first assignment as a programmer at IBM Research was to teach the scientist Fortran. It had just come out in April of 1957. I came in July, and there was going to be an edict in September that everybody had to use Fortran because it was an IBM product, and its own scientists better use it if they were wanting to have it as a product. And I had a very reluctant class of scientists, of research scientists, where it was my task to convince them that this was a great thing. So I want to talk about Fortran and then some other projects which involved a lot of concurrency in form of architectural parallelism that had to be dealt with also through compilers and languages. And then a little bit about some parallel computing work I had a group involved with later. This is the wrong way. Wrong button, sorry. The Fortran project, as those of you who know the history at all would recognize, is that was led by John Backus, and who died in March of this past year. And John set the goals for the project. There were two goals. One was increase user productivity, and productivity in writing code, debugging code, getting the answer, so that reduce the time and reduce the and improve that it took users to do that, and improved the assurance that it was right. Yeah, so not a lot of problems. And second goal was to improve the performance of the codes being written in Fortran, so the applications. And in fact, he was very specific about both of these. But the second one is to produce programs from the compiler. It was a language and compiler project. Produce programs almost as efficient as hand-coded ones, and do so on virtually every job. Okay? This was a very tall order in going from very primitive assembly code, and to about a fairly simple machine, in this particular case, a 704, getting to achieve these two goals, and he did it in a rather marvelous way. It turned out, just by teaching that course and understanding the compiler and the language and knowing the state of the art at that point, acquired these goals for the rest, kept these goals as my own goals for the rest of my career. All of my work after that was driven by those two goals. So that was a very important teaching assignment for me. Anyway, the language, it was, as I mentioned, was delivered in 57, and it was a very straightforward language. But one thing to note in terms of some of the languages that we have today that get in our way when we're thinking about parallelism on these multicores is the fact that the user, the language, did not specify really anything about where the data resided. The name of an object, like A, would have a residence, it would have a value, and if A happened, and if it could be a matrix, but the fact that it was stored row-wise or column-wise didn't matter in the language. There was, and so, though there was very quickly a decision was made about which way it would happen, but you could throw out that decision and store things instead of storing it column-wise or row-wise. And it featured then, as far as the compiler was concerned, the language itself was very simple. And it went from a very complicated specification, which was fortunate enough that somebody at MIT sent me a copy of a mimeographed copy of the original specification in 1953. But the features of the compiler itself were very interesting. This was a very early compiler, and the formal parsing techniques, one can see the emergence of that in one of the early papers that came out of this project. There was an intermediate language form for optimization. Here, we saved a seat for you. Not really, but it's empty. Thank you. And then the idea of having control flow graphs, a graphic way of expressing how the control was in the program, actually existed by those terms. There was a term common subexpression elimination was used. There was a generalized register allocator, even for only 3 registers. This was a huge advance at the time. And the word optimization that is applied to the transformations came from because it was an optimized register allocator in terms of the algorithm that they had put together. And it produced spectacular object code. In fact, it looked as if it was broken in some instances by the transformations that was made. So this is the base. So was a great start for a great language, and I'm glad to hear that it's being used here still. But I think I think we do need to go back to some of its basic principles and probably raise the level much higher for these multicores. Now, the next project that I was involved with, I wasn't involved with the Fortran project at all, just as teaching the scientist what to do with it, how to use it. And in fact, they were convinced. They didn't need an edict to use it because it did improve their productivity, and the performance was better than their hand codes in many cases. Now, the next project that I was involved with was a project called Stretch, which was started in 1955, but it got its name in 56. These are all IBM projects, and I'm talking about my experiences, not the whole history of the field by any means. It was my history. It's my history, so it's on a few of these projects. So the goal of Stretch was to be 100 times faster than any machine that existed, and they knew, the people involved, and I have a picture of Fred Brooks here on the left, in case you don't recognize him, who was one of the very important people on that project and drove many aspects of the project, including setting a lot of the goals of the project. And it turns out, I've come to realize in looking at some of these early projects, that setting goals really made a huge difference. Setting goals and sticking with the goals in order to in how the projects evolved. Anyway, back the main performance bottleneck that existed, and this to achieve this 100 times anything else, was the latency to memory, the bandwidth, and they could not do it without addressing that question. There was no possibility. That was recognized in 1955, and we're still working on that problem. So the bandwidth to the data, the latency to memories is still a problem, and we've put in layers and layers of caches and other mechanisms in order to solve it. And this machine, in fact, had its own, not caches, but its own ways of handling concurrency in terms of accessing the information. So it was an extraordinarily ambitious machine in all aspects. I was involved with the compiler, a part of the compiler. The other thing this particular machine had was a, whoops, I keep going backwards here, sorry. This comes first. The concurrency then, overcoming the slow speed of getting data to the computational units, was overcome by having interleaved storage accesses from these memories, six-way interleave. This is designed in 1955. It had an instruction look-ahead unit. We're still certainly building those, and have for many years since then. And it had a super scaler, which meant more than one instruction can be initiated within one major clock cycle. Though that, I have question marks there because that was never called out. The terms are different these days. And it was never called out as a feature. I just happened to find it in looking through the notes of one of the engineers fairly recently, notes that he used in teaching a class to other engineers at the time. It had multi-programming and lots of other features, including the look-ahead unit was able to support hard interrupts, precise interrupts. So it could be way ahead in the look ahead of the instructions, doing the instructions one after the other, and then some interrupt would happen, and because it was way ahead, it had to back out that the instructions and give the appearance of a precise interrupt taken at the time the interrupt would have been taken. So anyway, it was a very advanced machine, and a lot of things were invented then. But that wasn't all of the machine. The stretch machine was initially built for Los Alamos, and then there were several other machines that were built for weather problem, for weapons, missile tracking, and a few other things. But in addition, there was a project which I got involved with, which was for the National Security Agency. That was an unknown agency at the time. I read about it in the New York Times while I was on the project and had a Q clearance and hadn't been told what it was all about. Well, I was pretty dumb about not figuring out more than I did. But it was built for code breaking, and it was a machine that was totally different in design, probably than any machine any of you have seen, because for one thing, it was needed to be able to stream massive amounts of data collected from listening stations around the world. This is at the time of the Cold War, and through an analysis station on the machine, which was a big box bigger than Stretch, but it was under it collected up the statistics regarding the character, the information that was in the data streams, and it was really a pattern matching system over text, and the machine itself was designed with a perfect, at the clock level, major clock level, balance between the streaming collection of the information that allowed it to do pattern matching on the data, and the memory where that part of the machine picked up its data, and the I/O. So it could come in an I/O from the tapes, come into memory, stream through the streaming unit, and then where information was collected, and then go back out to, if necessary, back out to the specially designed tractor tape. So it was, and the part that I was involved with, and that was the only machine that had that sort of thing. As far as I know, it's the only machine that has ever been built that had that kind of balance between computation, memory, and data. My involvement with this was on helping to develop an alpha language, which was the language in which the people actually doing the code breaking. I knew nothing about it. That was couldn't even, that was very, very highly secret how they did it, what the algorithms were there. But where they could write their algorithms in a very high language and actually use the machine to do the work. And this language really was fit the problem and the machine, and to an amazing degree. And I recently, well, not so recently nowadays, but gave a lecture on this language out at Stanford, and in preparing for that lecture, I looked to see about DNA matching. Is how many instructions would it take for me to write in the alpha language, to do the standard DNA matching algorithm over masses of data, and I think I came to the conclusion that I could write in 12 instructions in this language. I could have done DNA matching over a great body of data, and it was really the right language for the problem. And if one had the machine, one could have still had the machine. It would have been, just a piece of cake. Really amazing. So that is where my background, as far as is where I come to the conclusion that if we're going to have massive parallelism, we're going to have the right language, and in today's terms, the right compiler to do the bridge. We're not going to get another machine quite like that. That's that much of a match. Though they're still working on such machines, and maybe what we need are languages that are very specifically domain specific, right? Machines and languages, because it's the bridge. I think it's the bridge in between. That's the hardest problem we have these days. The software that can take an application written in the right language and bridge it to a machine that has the parallel capability to deliver the performance that's expected. This is what the compiler, I was involved with the compiler, part of the compiler, looked like. And I'm putting this up because on the left hand, I think there's some interesting things to say about a multi-language, multi-targeted compiler, which is what we have today, not everywhere, and where we break down the functions of the compiler, the translator from the language. These were very different languages. Fortran, Autocoder 2 was, I guess, a business kind of language, which was related to COBOL in some sense. I didn't pay much attention to that at that time. And the alpha language that I had been working on, and into an optimizer, which is where one does through an intermediate form, which should have its own semantics, and and very precisely defined, I believe. Otherwise, you just get into messes of data structures and what it's going to look like. The same thing for all of these ILs, if you can have semantic levels of transformation from the high level to the low level. And then the optimizer, which does the analysis of the code of the program and the high-level transformations, and then the next one down where it's mapped to the low-level one-for-one kind of language that's needed to build object code. So, but I think that if we focus a little bit on compilers that are able to have semantic levels that lower the definition of the language closer and closer to the machine. You can start up very high, and as one goes down, understand the correctness of the code at each point, and in fact can actually, in some cases, provide opportunities for the user perhaps to get involved with tuning the code, though I'm not very keen on intermediate tuning of that sort, but it's probably necessary for many applications, but we've got to get the top up high first. Okay, so the outcomes of this particular project, I've got one more project to talk about. The outcomes of this was that it was a failure viewed by IBM because it was only it wasn't 100 times faster than any other machine. It was only 50% of that, and but the harvest machine was actually ran for 14 years until they couldn't get a replacement part for one of the tractor tapes, which was where all the data was stored, and so there was and nobody would build one for them, and so anyway, it was too bad. But it was very successful, and it had a huge influence on that system. Had a huge influence on the 360, the machine, which is where which was built next. Okay, where Fred Brooks went to from working on the Stretch project. He went to the 360 and brought with him not only the technologies here, but an understanding of how to build big projects and how to set goals. It's an astounding piece of work. I wasn't part of the 360 at all, but it's an astounding piece of work where he set the goals of not only on the machine, but on the architectural goals, and got buy-in on all of the architectural goals before they got started on the project itself. And the architectural goals were very, very detailed, and it's quite an interesting to look again, since I've become fairly goal-driven as a result of looking at these projects, to look how successful it was as a result of his way he handled that project. Okay, then there's one more project I want to talk about, and that's called the Advanced Compiling System Project. And this is a picture of John Koch, who is a person that made a major decision himself to move from high performance computing to trying to build the fastest machine in the world, machine that's in the world, to building machines that were cost performance. And that decision on John's part led to the PCs. Okay, to the RISC instruction set kind of thing. No longer trying to get the fastest machine, but to get a machine that had good cost performance. So John had been very much involved. On the Stretch machine, he had done this extremely hard look-ahead work, and was terribly disappointed about not being able to. That Stretch was, or the Stretch machine was not viewed as a success in IBM. Nice, interesting stories in there. But then, so he then got a small research project going to again build the fastest machine in the world. And this time, sometimes if you feel you failed the first time, you just go back and get it right the second time. And a bunch of us did get involved with this machine. I was involved with this also, and there we went after the pipeline scaler. We went looking for branch prediction. We did a lot of branch prediction and out of order instruction execution. 51 instructions in flight at the same time, if you like. You could tee them up, and loads and loads of instruction and data caches all over the place. So this was just, again, single instruction machine with handling vast amounts of concurrency in order to get performance. Much of it, of course, still the problem of fetching data out of memory. And I was involved here with the compiler, and this time we built the compiler first to try and develop the parameters on this machine, how many registers we could take advantage of, how deep, how many parallel ALUs, and if you're in architecture, you know all the stuff that you need to figure out ahead of time in order to balance the machine out in terms of keeping things, of cycle times basically is what it comes down to. And this compiler, which was an experimental compiler, referred to it that way, since it was built to drive the hardware design, we didn't know for sure what languages we'd use. For sure, Fortran was one of them. So we did had to build the machine, the analysis and the transformations and register allocator, all of that, very much in a parameterized way. And so we built, in the process of doing that and understanding what was needed in order to build a very parameterized system, we ended up being able to develop a lot of the theory and for program analysis and optimizations. But we were ready to do that because we'd already been through and had at least one big set of experiences with that. One of the things I was very pleased about was with this compiler is that we built the code was often faster than you could write by hand. We had asked, I guess it was Harando Kuke at the University of Chicago, and his students to have his students work on some of the numerical analysis codes, Kata and something others, and then they spent a summer doing it, and then said, oh, we can do this particular algorithm in 53 cycles on your machine. And so we just wrote it up in Fortran and ran it through our compiler, the experimental compiler, which had a timing simulator attached to the back end, and it did it in 47. So that was very pleasing, but it wasn't because we were paying knew anything about the algorithm in particular, but we knew we had built into the compiler, the experimental compiler, all the parameters and options that we could, knowledge we had about the problem that was the machine itself. We knew how to overlap huge amounts of things. We knew how to shuffle information between registers to keep from going back to memory and all of that sort of thing. So that was a very good experience. So this is the list of kind of familiar things that came out of that particular project, but I wouldn't say it came out of our work by any means. There was a lot of other work going on in the industry at the time and in the universities, and there was a great deal of collaboration. It was a great period in developing systems, and a lot of competition, of course, between different companies, and a lot of involvement of the students and universities, and it really drove the basis for a lot of invention in the compiler parts as well as in the machine architectures. So the next period, this takes one just kind of chronologically, takes one into the end of the 60s, when the project itself, this ACS project, was canceled, predictably. IBM had just bet the company on 360, and they didn't want this this big project, ACS, competing with it, because it wasn't based on the 360 architecture whatsoever. They couldn't afford it. In fact, at that time, it made no sense from a business point of view. Anyway, but it was a great project. So having failed once again, and shipping something to market, excepting for the harvest, which was never really, nothing much was classified right from the beginning. I wrote on harvest, I wrote the final report on the languages and the compilers, and immediately got stamped confidential, do not read, and I never had a copy of it. So I was pretty dumb about not making a copy before it got submitted. But anyway, so in the 70s was really a consolidation at least from my point of view and within IBM, of a lot of the things that we have been learning. And it was a fairly conservative period in terms of the kinds of machines we were building, at least, though there was a lot of other interesting things going on. But some of the giant steps that we had been looking at where we needed to mainstream. And that sometimes happens. One sees these cycles in a product lines, or even in research. You could see a nice breakthrough, and then there's a lot of kind of more work done to improve what has been discovered or put forward, and then the cycle will kind of get smaller and smaller in terms of the impacts of the work and the results, and then suddenly something new will come up, a new idea, and I think multicores is the thing that's going to really stir this whole field now. But in this period, then there was a number of things, and including John Cox's move, changing his own personal goal to building a system that had cost performance, not just high performance. And my own work went through a period of actually, I always like in my own work to not only do the research, the kind of interesting work on interesting new ideas, but more than anything else, I like to see them in products, and I have always kind of worked on both sides, and so during that an interim period there, and continuing into this project I'm going to talk about next, I got quite a bit of we got a lot of our technologies into the IBM systems and into the compiling projects that are still visible in IBM. The net. The next thing that came along, though, for me, was IBM, who had been quite late in getting into parallelism. There was a lot of wonderful work going on in parallelism starting in the late 60s, maybe even early 60s, the University of Illinois and elsewhere having great projects. And IBM in the mid 1980s kind of woke up and said, we better get into this. Now, there had been vectorization some before then. I don't quite know. Sam, you probably know more than I do about just when IBM got into the vectorization part. But I've forgotten that.
There was a Fortran I almost want to say one of the 390.
Yeah, it was. Right.
Sometime, it was in the early 80s. I remember reading.
Early 80s, yeah. It was before we got this going. And so this project, then, I was asked to look at. And this project was asked. I was in research, and somebody one of the managers came to me and said, "Okay, you have to. We've got to get into parallelism." And so I got, and I was asked. So I put together a group. I went to various universities and hired some people, including at the University of Illinois. Okay. And then we got in, and we built did some research, we built some compilers, and then did and some things with the runtime. So, but many other people have been working in this whole area, and so we had our own contributions, and it was a terrific group of people. There were people that both were great compiler builders. There were people that were great algorithm people, and it was wonderful to put together a new group and I just kind of let them go. I didn't contribute a whole lot to this, other than whenever somebody came in with saying they had this wonderful algorithm, and I would say, well, how are you going to implement that? Or if they came in with this wonderful piece of code, I would say, is there a paper here? It was just, prodding them in both directions, because I think both are important for progress in our field. Okay, one of the things that I also learned out of this, and it was an automatic parallelism, basically for Fortran, much of it for Fortran, though we tried to do it in other contexts, is that disambiguating data references is really hard. And one can do it for Fortran, but not very easily. But for languages with pointers, it's just impossible. C, to me, was the biggest setback for high-performance automatic compilation that ever happened. Sorry about that. And it allowed the user and required the user to take over the management of the storage of data. Not the values of data, the values will happen, but of the storage of data. And caches are another huge problem. I mean, the software people didn't invent those. The hardware people kept making them more and more and more complicated, and particularly with increased parallel CPUs and sharing of caches and all the cache protocols and the depths of caches. And you never knew where something was, whether it was in its proper, whether you could trust the value of the data, or whether the data, whether you had the right data in the right place. The other thing that one can't need, the procedure boundaries are an issue, of course, and just the reuse of storage and the ownership of data. Now, lots of data doesn't have to be owned by anyone if it's read only. So the languages took away the options for doing good work with the data from the compilers. And forming useful parallelism is a challenge. That's a different subject. There's been some nice work there. And so I'm going to skip this, I guess, because this was. But the bottom line here is, the question is the bottom line here, are data-centric languages the low-hanging fruit that we need to look at? And that, in the Purdue conference, and I'm sorry I don't remember the name of the person some of you probably attended that conference, is here in the spring. That was an issue that was raised, and I find it very compelling. Are languages that are data-centric rather than computation-centric, is that where we should be looking for the next answer to how we're going to deliver performance on the applications and at the same time, of course, productivity for the user productivity. And I believe it's going to be there. And I've heard people say that, other people say that, it's not, but nobody quite knows what it means, including myself. So that's a piece of work I think we need to look at. So this is kind of a repeat of that, some of that. And then if we could do that, we could have compiler techniques, a whole new branch of compilers that would allow us to manage data. Specifically, form the locality that will allow the streaming of data through a computational unit or through the cores, and do that in the presence of parallelism. We also need to influence the architects before it's too late, because they're hard at work now making things more and more complicated for us. So we better get busy. And really remember these goals. That's what it's about for people in the software business. It's really about user productivity and application performance. So that's the challenge of this next generation here, and is to try and make some headway on, I think, along these lines, but on the multi-core challenge, which is going to quickly turn into a huge mess if we don't. But it's going to take us a long time to get everything in place. However we decide to solve it, get things in place. These things will take 5 at least or 10 years. We're going to have to also, I mean, in the meantime, there will be lots and lots of programming work poured into making all of the things that run on desktops and laptops and all of the other gadgets we have faster or higher performance. But that work will not involve user productivity. Okay, thanks very much. I've been getting assigned from.
In the interest of time, since some of you have classes to go to, we'll pause for a few moments, and if you have some questions for Fran, then we can ask them after the room has settled down a little bit. So thank you again.
Thanks.